All right, here's the recording in progress. I'll share the screen. All right, so I should be back to regular schedule, synchronous meetings. Of course, many of you are still not just watching the video later. That's okay. I was finished with 3.2 from Monday and Tuesday, so we're up to 3.3. So 3.3 today and tomorrow. Quiz on Friday will be on 3.2 and 3.3 material. Okay, so I was pretty much done with 3.2 from the last 2 days. So let's get started with 3.3. All right, so 3.3, we're doing polynomial long division. You might remember some of this from your intermediate algebra. So finding factors and zeros of polynomials, page 145 is where we're at. Okay, let's check the homework assignment. Minor 3.2, I changed the homework to 7 to 33 odd. So it looks like 3.3, you have 1 to 27 odd and 33 to 37 odd. So let's get that review right now. Page 154. Okay, so for the benefit of those of you that don't have the book and aren't getting it, let me go like this. I think you can see it like that. I can move this over a little bit. Yeah, okay, and then go like that. Okay, that does it. And then on this page, how far do we have to go? 37. Okay, so I think that should show you all of it. Yeah, okay. Okay, so we're doing polynomial long division. Find a quotient and remainder when a polynomial is divided by some other polynomial. Okay, so this part hopefully is mostly a review of what happened in your intermediate algebra class, perhaps. Okay, so polynomial long division. Again, ignore any dates that you have here. So P of x is 2x squared plus 3x minus 3. D of x, denominator, is x minus 2. All right, so you might recall long division goes like this. Kind of like long division of numbers. You put the 2x squared plus 3x minus 3 on the inside, and thing you're dividing by goes out here, the divisor, x minus 2. Okay. All right,
You're just going over 1 through 6, but this isn't part of our homework, right?
this is part of our homework. Yes, it should be. From 3.3.
Didn't you just say 7 to 33?
I'm doing 3.3 now, Bonnie. I was finished with 3.2.
Yeah, I know, but didn't oh wait, oh wait a minute. Oh, I see. Okay.
Yeah. So
okay, sorry.
The last 2 days videos were on 3.2. Okay. All right. So how do I divide this? You take the first thing here and the first thing here. Look at the x and 2x squared. So the way the game works is first thing here, and I ask myself, what do you multiply this by to get that? So what do you multiply x by to get 2x squared? 2x. So I put the 2x on top, and you should line everything up. Notice these are dedicated columns. These are all constants. These are all x's. These are all x squared. All the way down, this is x squared. All the way down, this is x. All the way down, these are numbers. Okay, 2x. Now I'm going to take that 2x and multiply it by this whole thing. So 2x times this whole thing is 2x squared minus 4x. Subtract. Okay, this is a little bit tricky, but it's minus parentheses, and then you subtract. Okay? But if you stop and think about what you did in arithmetic, long division and arithmetic, right? When you did long division back in, I don't know, 5th grade or something like that, when you did all this stuff, you subtract, right? So minus parentheses. This minus this is nothing. Got to be careful here. 3 minus a negative 4 is 7x. Bring down to minus 3, just like long division of numbers, and start all over. Okay, so how do I go from this thing to this thing? First thing here, first thing here. So x times what gives me 7x? 7. So plus 7. Now I go 7 times this whole thing, 7x minus 14. Subtract in parentheses. You've got to be careful that you're subtracting. Okay, that minus that is nothing. Negative 3 minus a minus 14, negative 3 plus 14 is 11. So 11 is my remainder. So I write my answer as plus 11 over x minus 2. So remember how you did long division of numbers, right? remainder goes up here, and the divisor goes here. Okay, so remember when you're in 5th grade, let's pretend the remainder was 5 and you're dividing by 9, then you put 5/9, right? So same thing here, remainder over the original divisor. Okay. The one tricky thing though is by convention, you're supposed to put the plus there. Don't leave it like this, that's technically incorrect. Okay. Now, when you were doing arithmetic and your answer came out to be, let's say 4 5/9, right? Remember when you were doing that? Maybe even before that, you just put R, remainder 5, right? Then after you got more sophisticated, you say, oh, 5/9. Divisor is on the bottom and the remainder is on top. Now, when I write this, 4 5/9, everybody knows it means 4 5/9, right? You don't think of this as 4 times 5/9. However, once you have algebraic symbols like X's all over the place, if you don't put the plus sign and just write it like this, right? 2x plus 7, 11 over x minus 2, the normal inclination is saying, oh, we're doing algebra. There's no symbol between here and here. You must mean multiply. We don't, it means addition. So for these polynomial long divisions, you must put a plus symbol, unlike over here. Okay, remember in arithmetic, you didn't have to put 4 plus 5/9, right? Because when you just look at that, everybody knows it means 4 5/9. Nobody thinks of this as 4 times 5/9. Okay, but in algebra, right, you see all these, oh, I see all these x's all over. We're doing algebra. And so, oh, there's no symbol between 7 and 11 over x minus 2. You must mean multiply. But no, we mean to add. So therefore, you have to put the plus there for the answer. Okay. Alternatively, you can put a minus if the remainder came out to be negative. Let's pretend this came out to be a negative 11. You are allowed to put minus 11 over x minus 2. Okay. So there's a polynomial long division that hopefully we did before. And I'll show you several more examples of this. Number 3, x cubed plus x squared minus 2 divided by x minus 1. Okay, so we know the way it works. This is on the inside, this is on the outside. Okay, now before going on, notice anything different about how I wrote this and what I wrote here. The original goes x cubed plus x squared minus 2. There was no x, like there wasn't a 3x or minus 5x or something like that. If that's the case, you have to sneak in a 0x. Otherwise, it won't work. You got to have a dedicated column there. So when I write this out, x cubed plus x squared, I must put 0x minus 2. I need a space for the x column. Okay. True, there may be no x in the original, but x sure pops up as I develop the problem. It shows up everywhere. Okay. I mean, it's kind of like when you're writing the number, what, 1,102, the 0 has to be in the tens place, right? If I say 1,102, right? I'm not allowed to write it like this, right? Because everybody thinks of that as 112. You can't just say, oh, that's 1,102 ones. No, you need a placeholder, right? So I look at this and I say, oh, now I know this is 1,100, no tens and 2 ones. So similarly, 1x cubed, 1x squared, no x's, and a negative 2. Then you're good. Just box this out that this was just a timeout here. All right, then the rest is the same. First thing here, first thing here. How do you go from x up to x cubed? Multiply by x squared. Now you go x squared times this whole thing. X squared times x is x cubed. X squared times negative 1 is negative x squared. Subtract in parentheses. Okay, gotta watch out for that. It's a little bit tricky. Okay, this cancels out. Okay, real careful here. X squared minus a minus x squared. That's x squared plus x squared, 2x squared. Bring down to 0x. You might say, do I have to bring that down to 0x if it's a 0? Yes. Think of when you did long division with numbers, right? You did long division. If there was a 0 to come down, you brought down to 0, didn't you? So it's the same thing. So even if it's a 0, just bring it down. Okay, start all over. This into this. Very analogous to what you did long division of numbers, right? Whole numbers. What do you multiply this by to get that? 2x. So plus 2x. Now you go 2x times this whole thing. 2x times x minus 1, 2x squared minus 2x. subtract parentheses again, watch out. This cancels out. 0 minus a minus 2 is plus 2x. Bring down to minus 2. Do it all over again. How do you go from here to here? How do I go from x to 2x? Multiply by 2. Plus 2. Now take 2 times this whole thing. 2 times x, 2x. 2 times negative 1 is negative 2. Subtract. Well, we already know that anything minus itself is 0. So this has no remainder. So this is a case of no remainder, right? So this works perfectly. So over here, there was a remainder of 11, right? Here, there is no remainder. This works out perfectly. Just like when you did division, 35 divided by 7 is 5. 36 divided by 7, you say, oh, 5 remainder 1, or 5 and 1/7, right? So something similar works out here. Okay, so this is polynomial long division. And one other thing to note, I won't bother to check it, but just think of the way division works. If this is the correct answer, then this thing times this thing should be this, the original. You can try it on your own. But that's just the same thing as like when you did this, right? 35 divided by 5 comes out to be 7. That means the same thing as 5 times 7 is 35, right? Back in arithmetic. So likewise, if this divided by this comes out to be that, then if I take these two and multiply them together, I should get this back. That's the way you can double check. Okay, 5 is the next one I was going to do. It's a little bit longer. But looking at the work, maybe it's not so long after all. So 2x to the 4th, blah, 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 divided by x squared minus x minus 1. Okay, so the 2x to the 4th stuff goes inside, x squared minus x minus 1 outside. Okay. And I'm noticing you had to do 1, 3, and 5. I'm doing them all right here. So again, when we say you have to do 70% of the homework on the, for the test, it's kind of a joke because I do a great percentage of them anyway. I'm literally doing all of 1, 3, and 5. Okay, first thing here. What do you multiply this by to get 2x to the 4th? Well, you need a 2 and an x squared. I put it in the x squared column. So 2x squared. Now I go 2x squared times this whole thing. So 2x squared times x squared, 2x to the 4th. 2x squared times negative x is negative 2x cubed. 2x squared times negative 1, negative 2x squared. Parentheses, subtract. Cancels out. This one also cancels out. Negative 2 minus a minus, so plus 2, that also cancels out. And 4 minus a minus 2 is 6x squared. Bring all the rest down. Start all over again. How do I go from x squared to 6x squared? 6 plus 6. Now 6 times this whole thing. 6 times x squared, 6x squared. 6 times negative x, negative 6x. 6 times negative 1, negative 6. Subtract, minus parentheses. 6x squared minus 6x squared, 0. X minus a negative 6x, x plus 6x, 7x. Negative 2 minus a negative 6, gotta watch out for all these double negatives. Negative 2 plus 6, 4. So this whole thing qualifies as my remainder. And by the way, you say, how do you know when to stop? Well, when you reach that last item, right? You're finished, there's nothing more, so you stop. So remainder, original divisor. So plus remainder, 7x plus 4 over the original divisor, x squared minus x minus 1. And again, by convention, you do need the plus. So if I don't see the plus, I can take out points for that. You're not supposed to just do it like this. Please understand that, right? So that's not quite the same as in arithmetic, right? In arithmetic, you just wrote 4 and 5/9. Everybody knows that means 4 plus 5/9. Nobody interprets that as 4 times 5/9. Okay? But in algebra, right, one could easily interpret this if you don't put a plus here, right? You say, oh, I see x's everywhere. I must be doing algebra. There's no symbol. This must mean multiply. But no, I want addition, so that's why for the remainder, you should put a plus, and then the rest is the same. Remainder over divisor. Okay. So that's that. Okay, so that's 1, 3, and 5. Now I will digress a little bit just to show you an important principle. So let's go back to problem number 1, where p of x, the original polynomial, was 2x squared plus 3x minus 3, and the divisor was x minus 2. And they're telling me to divide by x minus 2. Let's just see what happens if I plug in 2, not -2, but 2. So where'd you get that from? Well, I kind of got it from here, but just do it and see what happens. Plug in 2 here, 2 here. 2 times 2 squared plus 3 times 2 minus 3. 2 times 2 times 2 is 8. 3 times 2 is 6, minus 3. 11. What do you notice about the 11? That turns out to be the remainder over here. Does that always work? Let's try number 3. Here's the original polynomial. They told me to divide by x minus 1. I'm going to see what happens when I plug in 1, not -1, but 1. P of 1 to this polynomial. Well, that's easy. 1 cubed is 1. 1 squared is 1. 1 plus 1 minus 2, 0. That was the remainder over here. All right, so that leads us to something called the remainder theorem. And you may want to put this on your next cheat sheet. When a polynomial p of x is divided by x minus a, then the remainder equals p of a. Okay, if you want to know the remainder very quickly, rather than doing all this long division, just plug in a to the original polynomial. Be careful, there's a sign change here. Okay, so it says when you're dividing by x minus 2, plug in 2. If you're dividing by x minus 1, plug in 1. But if I were dividing by x plus 1, I would plug in -1. That's the way it works here. When a polynomial is divided by x minus a, the remainder equals p of a. And then there's an obvious result of that. Okay, for the case like number 3. Let's say if you were to plug in a number, you get 0. That means there's no remainder. So that goes along with something called the factor theorem also. If p of a is equal to 0, then x minus a is a factor of p of x. Okay, so a fast way to determine if this binomial is a factor of p of a is just plug in, and if you get 0, x minus a is a factor of p of x. You might want to see this in the text also. Like the text version instead of the Melvin Hum version. It's similar. Page 148. If the polynomial p of x is divided by the linear factor x minus c, the remainder is p of c. Okay, if all you want is the remainder, you can just plug in c to the polynomial. The linear term x minus c is a factor of the polynomial p of x if and only if p of c is equal to 0. Okay. So rather than doing all of that long division, if you want to just plug in, if you end up with 0, then you know that you have a factor. Okay, x minus c turns out to be a factor. Okay, so if you want to put this on your cheat sheet, you may. It's on page 148. Or my version is similar. Okay, when a polynomial p of x is divided by x minus a, the remainder equals p of a. This is a consequence of that. If p of a is 0, then x minus a is a factor of p of x. Okay, so let's try, for instance, number 7. Use the factor theorem to show that x minus c is a factor of p of x for the given values of c, and then factor p of x completely. Okay, so what do they mean by that? So for number 7, they say c is equal to 1. first plug in 1. That's easy. 1 cubed is 1, 1 squared is 1. So 1 minus 5 plus 8 minus 4 comes out to be 0. What that now means is that x minus 1 is a factor of p of x. So if I plug in 1, I get 0. That means x minus 1 is going to be a factor. So if I take the original polynomial, divide by x minus 1, I should get no remainder. Okay, so let's do it. So how many times is x going to x cubed? X squared. So x squared goes up here. Now x squared times this whole thing, x cubed minus x squared. Subtract, that cancels out. Negative 5 minus a minus 1, negative 5 plus 1, negative 4x squared. Bring down to 8x. Do it again. What do you multiply x by to get negative 4x squared? Negative 4x. Now negative 4x times this whole thing, negative 4x squared plus 4x. Subtract. These cancel out. Negative 4 minus a minus 4x squared, 0. 8x minus 4x is 4x. Bring down to minus 4. How many times is x going to 4x? 4 plus 4. 4x minus 4, no remainder. So that means my original polynomial is x minus 1 times that. The original polynomial, x cubed minus 5x squared plus 8x minus 4, is x minus 1 times x squared minus 4x minus 4. And that you should recognize is easy to factor. It's x minus 2, or x minus 1, x minus 2 squared. Okay. So that pretty much does it. Okay, the problem is finished, but if you want a quick graph of that, you can start off with n behavior. Remember I talked about n behavior? Okay, plug in 100. It's positive, that's positive. So this side it goes to positive. Over here, if I plug in negative 100, negative, positive, so this side goes down. And then I use the rule that if you have a multiplicity of 1, the graph crosses the x-axis. So at x equals 1, this side is down, this side must be up. So this is the whole graph. Ends up doing something like that. Okay. All right, 11 is a little bit harder because I see they give us a fraction. P of x is 3x cubed plus 3x squared minus 8x plus 4. C is equal to 2/3. Okay, 2/3, if I plug it in, is supposed to be 0. Okay, it's kind of hard. Let's see if that's the case. So P of 2/3 as a function, 3 times 2/3 cubed plus 2/3 squared minus 8 times 2/3 plus 4. So 2/3 cubed, 2/3 times 2/3 times 2/3, 8/27. Cancel 3/27, giving me a 9. 2/3 squared is 4/9. 8 times 2/3 is minus 16/3 plus 4. So common denominator looks like it's 9. 8/9, 4/9, minus 16/3 multiplied by 3/3 to get a common denominator of 9. And 4 is like 4/1 multiplied by 9/9. So my common denominator is 9. So on top I have 8 plus 4 minus 3 times 16 is 48. So minus 48 plus 36. Punch this in the machine if you want. You do end up with a 0. Okay. The theorem says that means x minus 2/3 is a factor of P of x, but I don't want to divide by x minus 2/3. The trick is to make this nice, just multiply by 3. 3 times x minus 2/3 is 3x minus 2. 3x minus 2 should be a factor of P of x. Okay. So in other words, if you end up with a fraction like this, just multiply by 3 and you get a factor. If you're not convinced of that, let's try it. Okay, so let's actually try the long division now. So 3x minus 2 divided into the original 3x cubed plus x squared minus 8x plus 4. Okay. So here we go. What do you multiply that by to get that? X squared. Now x squared times this whole thing, x squared times 3x cubed, x squared times negative 2, negative 2x squared, minus parentheses, subtract. This cancels out. X squared minus a negative 2x squared, x squared plus 2x squared, 3x squared. Minus the 8x, start all over. How do I go from here to here? From 3x to 3x squared, multiplied by a positive x. Now you take x times this whole thing. X times that is 3x squared minus 2x. Subtract in parentheses. Looks like this cancels out. And you got to really watch out all the double negatives. Negative 8 minus a negative 2, negative 8 plus 2, negative 6x. Bring down to 4. Do it again. You say, when do you get to stop? Well, you stop when you reach the last term. I reached a 4, right? So that means I know I can stop. Just like when you're doing long division of numbers, right? They give me some super big number to divide 316,521, whatever. You just keep going until you reach that last number, right? It's the same thing here. Okay. First thing here, first thing here. How do you go from there to there? From 3x to negative 6x, I need a negative 2. Now, what's negative 2 times this whole thing? Negative 2 times 3x is negative 6x. Negative 2 times negative 2 is a positive 4. Anything minus itself is 0. So it factors perfectly, just as we anticipated it to. So that means my original polynomial, 3x cubed, blah, 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 is now 3x minus 2 times x squared plus x minus 2. And now that's pretty easy to factor, right? Looks like you can have a 2 and a 1 with a plus and a minus. So the complete factorization is 3x minus 2, x minus 1, x plus 2. And that's about it for that one. Okay, as you might anticipate, for stuff like this, if we completely factor, well, a third degree polynomial, there should be 3 factors, right? X minus something, x minus something, x minus something, right? Although you might have repetition. Same thing here. Third degree, there should be 3 factors. There they are. And that means 3 roots, also 3 solutions. Solutions are roots, R-O-O-T-S. We'll use that language. Solutions. Same as root. Okay, so let me show you in the text now something involving this. Okay, let's see, rational zeros test, I'll come back to that. Finding zeros of a polynomial. Okay. When a 0 is found, I'm going to hold off on this because I haven't talked about the rational zeros test yet, or the rational root theorem. When a 0 is found, that means when you plug in a number, you get 0. Factor p of x and repeat the process on the quotient. There's no need to check possible zeros of the quotient that have already been eliminated from the list of zeros, but check any zeros that have been found because they may have a multiplicity greater than 1. Once p of x has been factored to linear and quadratic terms, use a quadratic formula if necessary to factor the quadratics. Okay, this is on page 152. You can put this on your cheat sheet or not. I don't really think you need it if you know what's going on. Okay, but the idea is this. If you have, let's say, 4th degree, there's going to be 4 zeros. If you have 3rd degree, there's going to be 3 zeros, and so on. Okay, if you have something as bad as 5th degree, you're going to have 5 zeros, and that also means that's how many factors you have. you can write it as 5 factors. Okay. So if you have fourth degree, there's going to be, 4 factors, x minus something, x plus something, 2x plus something, x minus something, right? That's the way it's always going to work. You have as many factors as the degree. So if you have, let's say, 6th degree, there's going to be 6 zeros. If you allow for multiplicity, if you allow for repetition, we talked about multiplicity before. We'll talk more about it. So there's going to be 4 zeros and 4 factors. Okay, so we already know that to be the case. Okay. All right. Now, an introduction to something called the rational zeros test or the rational root theorem. Okay, so what is the rational zeros test or the rational root theorem? Okay, I'll show you the text version. It's correct. I'll give you my version also. It's on page 150. Suppose P over Q is a rational zero of this mess. So it's a rational number, integer divided by integer. If you plug in this thing, you get 0. Then P divides A sub 0, Q divides A sub n. A sub 0 is the constant. A sub n is the leading coefficient. The rational zero test provides a list of possible rational zeros. Okay, this is correct. I'll give you my version. So it's called the rational zeros test, or sometimes the rational root theorem. I'll use both. Given a polynomial P of X, if there are any rational zeros, then they are of the form plus or minus a factor of the constant term, P, divided by a factor of the leading coefficient, Q. That's exactly what the text means here. A factor of the constant, factor of the leading coefficient. Okay. I might just have time to show you a couple of these, and then that's about it, because we're running out of time shortly. All right, 13, x to the 4th plus blah, 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 is 4 equals 0. List the possible rational zeros. Determine all the possibilities for rational zeros. What you need are just the constant term and the leading coefficient. So when I do these problems, I don't look at anything except the first and last. Look at the x to the 4th, coefficient of 1, and the constant is 4. Just completely ignore everything else. I don't know if they can go like this. Yeah, just look at this and look at this. There's a 1 here, there's a 4 here. So here's the way the possible rational zeros work. Plus or minus, the numerator is a factor of the 4, the denominator is a factor of 1. Well, what are the only factors of 1? 1. What are the factors of 4? 1, 2, and 4. So this rational zeros test says the only possible rational zeros are plus or minus 1, 2, or 4 divided by 1. Well, if you divide by 1, you just don't put it. So plus or minus 1, plus or minus 2, plus or minus 4. These are the only possible rational zeros. Now, we're not guaranteeing that any of these work, but those are the only candidates. Now, that's a lot. That's 6 numbers to try, right? Plus or minus 1, plus or minus 2, plus or minus 4. That's 6 things. Well, that's a lot smaller than infinity. All right, that means from the start, I don't have to plug in 3. It isn't going to work. I don't have to plug in negative 80. It isn't going to work. I don't have to plug in 2/3. It isn't going to work. I don't have to plug in negative 1/2. It isn't going to work. The only things that might work are these. Now, we don't know that any of these are going to work either. But we're saying if there's a rational zero, it has to come from this list. Okay? Think of it as like, it's almost like running for office. Okay, these are the only ones that are running for office. So did all the other numbers are automatically excluded. These are the only ones running for office, but none of these still might win, so to speak. Okay, but if you're not running for office, so to speak, you're automatically not in the game, right? So here are the only candidates to try. Okay, but they still might not work. But these are the only candidates. If there are any rational zeros, they have to come from this list. Yeah, question.
No, I wasn't gonna say a question. I was gonna say something, but I see your work later on. I see you're gonna go over it anyway, so I'll just
Yeah.
be quiet.
Yeah, I'll go over another one. Okay, 15 is a much harder problem. Right, so 15, they say give all the possible rational zeros. Okay, this is really going to be long, as you might guess, because of the 10 and the 4. So they got 10x to the 5th minus 14x cubed plus 18x squared plus 6x minus 4 equals 0. What are the possible rational zeros? Okay, so again, the only things you need to look at are the leading coefficient, 10, and the constant, -4. You might as well just pretend it's 4 because you're doing plus or minus anyway. So 10 and 4. The possible rational zeros are plus or minus a factor of 4. You don't have to say -4 because you're doing plus or minus anyway. Divided by a factor of 10. All right, what are the factors of 4? 1, 2, and 4. What are the factors of 10? 1, 2, 5, and 10. Okay. This is going to be longer. How do I write my list? You take everything on top and divide it by everything on the bottom. In other words, you take 1, 2, and 4, divide them all by 1. Of course, if you divide by 1, you just leave them alone. So there it is, plus or minus 1, 2, and 4. Then I take everything on top and divide it by the next factor on the bottom, 2. So 1, 2, and 4 divided by 2. So plus minus 1/2, plus or minus 2/2, plus or minus 4/2. But I crossed these out because I noticed that's a repetition. What is 2 over 2? 1, I already got it. 4 over 2 is 2, I already got it. So I can cross these out. There's nothing new there, so to speak. Then I take the same 3, 1, 2, and 4, divide them by 5, throw out any repetition. So plus or minus 1/5, plus or minus 2/5, plus or minus 4/5. It does not look there was any repetition, so I got to keep them all. And finally, same thing. Take the 1, 2, and 4, divide them by 10. So plus or minus 1/10, plus or minus 2/10, plus or minus 4/10. But why did I cross off plus or minus 2/10 and plus or minus 4/10? Because 2/10 is the same as 1/5. I already have it on my list, so I don't have to write it again. And likewise, plus or minus 4/10 is the same as plus or minus 2/5. I already have that on my list, so I don't have to worry about that. Okay. Okay, now 17, we do not have integer coefficients. In order for me to use the rational zeros theorem, oops, all the coefficients have to be integers. Like you can't have 2/3 as a coefficient or 1/2 or pi. They have to be integers. Nice. So what if they give me a problem like 17? I got fractions. Well, change it so there is no fraction. I can do that if I simply multiply both sides by 2 before I start. Right? So for 17, possibility of rational zeros, here's the original, 3/2 x cubed minus 5/2 x squared, blah, blah, blah. I will simply multiply both sides by 2. So that I have integer coefficients. 0 times 2 is 0. 2 times this is 3x cubed. 2 times that is -5x squared. Double that, 14x minus 8 equals 0. Now this is the way that I want it. So now this is good to go. So my possible rational zeros, plus or minus factor of 8 divided by factor of 3. So again, in general, factor of the constant term on top, factor of leading coefficient on the bottom. Plus or minus. What are the factors of 8? 1, 2, 4, and 8. What are the factors of 3? 1 and 3. All right, so I'll take 1, 2, 4, and 8 divided by 1. Oh, we divide by 1, just leave it. So there it is, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. And then do the same thing except with 3 in the denominator. So take 1, 2, 4, and 8 and divide them all by 3. So plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, plus or minus 8/3. Okay, so the quote unquote only candidates to try that will work for this are from this list. Granted, that's 16 possibilities. 1, 2, 3, 4, 5, 6, 7, 8 times 2 is 16. You only have to try these 16. No other rational number will work. You don't have to bother trying 5. You don't have to bother trying 3. You don't have to bother trying -3 or 5/7. They're not going to work. Now, none of these might work still. They're the only candidates. Doesn't mean that any of these will work. We're saying if there's any rational solution, if there is a rational solution, it must come from this list over here.
When the text asks about irrational zeros, those only come into play when when you are done factoring and there is an unfactorable portion, right?
Correct. So
Okay.
when you get to this part and say, where do I do the irrationals? That's when you're left with a quadratic like x squared minus x minus 1 or something like that. You can't factor it. Then you have to use the quadratic formula to get irrationals. Correct. And that will come into play also when we have to get complex solutions, the I stuff, the square root of negatives, which will come into play also. So we'll definitely have to worry about that too. Okay. All right, but for now, that was as much as I was going to do. So let me stop the share and check the chat. So 9:53-ish. Okay, so I'll take any questions, and if there are no questions, we're going to call it a day. So let's see, on our paper, I can't show it to you anymore. Let's just switch back. But we're doing 3.3. I'll do a lot more 3.3 tomorrow. And Friday will be a quiz on 3.2 and 3.3 kind of material. Okay, I see it's about 9:53. Anybody have a question? Otherwise, we're done for the day. Wait just a moment. Okay, I don't see anything or hear anything, so that's about it. All right, so we're done, folks. We'll continue this tomorrow. Okay, bye, everybody. Have a good day.
Thank you, you too.